Hi students, this is a lecture on section 15.1, which is about double integrals over rectangles. So for double integrals, rectangles are the easiest type of double integral to do. And double integrals are a lot like partial derivatives in that you're going to be treating the other variables as constant and you're only going to be integrating with respect to one variable. And the first type of double integrals over rectangles that we're going to be dealing with are called iterated integrals. Okay, so for our first example, let's evaluate each iterated integral. Okay, evaluate each iterated integral. And what iterated means is they have it already set up for you with the variables. So basically, it'll be a double integral, but you're going to do your innermost variable first, and then you work your way outward. Okay, so iterated means you do your innermost integral first. Okay, so you work from the inside outwards. Okay, and what does a double integral look like? Well, you actually just write the integral symbol twice. Okay, so for our first example, we're going to be doing the double integral. So it's literally just the integral symbol written twice. Okay, and for this one, we're going from -1 to 2. For the outer integral, and then we're going from 0 to 1 for the inner integral. Okay, and then our function is a multivariable function, which is 20x to the 4th y cubed dy dx. Okay, so the integral from -1 to 2 and the integral from 0 to 1, double integral, of 20x to the 4th y cubed dy dx. So iterated means you do the inner integral first. So here the inner integral is dy. How do I know it's the inner integral? Well, it's the dy is written first, so that means it's on the inside. Okay, so here our inner integral is this one right here. I'm circling it in red. Okay, so what we want to do is we want to do the inner integral first, and then because it's with respect to y, that means any other variable is treated as a constant. Okay, so since the other variable here is x, and we're doing it dy, that means x is a constant. Okay, so the dy means x is a constant. A lot like a partial derivative, right? When you do a partial derivative with respect to x, all the other variables are constant. If you do an integral with respect to y, all the other variables are constant. So same idea. Okay? So since 20x to the 4th is constant, we're really only integrating y cubed dy. Okay, so what we got here is I can just factor out the 20x to the 4th. And then our inner integral is just going to be the integral from 0 to 1 of y cubed dy. And of course we have our outer integral, which we're not really doing anything with yet, but that's -1 to 2 dx. But now I'm going to go ahead and do this inner integral. As you can see here, I factored out the constants, so this is the only part that I have to integrate, is the part that involves y. Okay, so that's our inner integral, and here we can just use the power rule. So remember, the power rule says that if you're integrating a power, you add 1 to the exponent and you divide by the new exponent. So that's going to be y to the 3 plus 1 is y to the fourth, and we divide by the new exponent. So it's going to be y to the fourth divided by 4. And for that right there, we want to evaluate that from 0 to 1. And when I say from 0 to 1, because the original variable that we did for the inner integral was y, that means from y equals 0 to y equals 1. Okay, so actually in this original problem, because the inner integral was dy, that's actually the same as saying y equals 0 and y equals 1. Whereas our outer integral is x. Okay, so the outer integral is x equals -1 and x equals 2. Okay, but here we're going to be plugging in 0 and 1 for y. Okay, so, and remember when you're doing an integral, you start with the top number first, you plug it into the function, and then you subtract the function value at the bottom number. Okay, so that's going to give us 1 to the fourth over 4 minus 0 to the fourth over 4. And all I'm doing right there is the inner integral. We still have this other stuff going on the outside. I can write it in if I want, but it's not necessary. But keep in mind that you still have the integral from -1 to 2 of 20x to the fourth dx on the outside. But we're only doing the red part right now because we need to simplify it. Okay? So, so what we do next is we simplify this. So 0 to the fourth is just 0. So the second term is just 0. And 1 to the fourth is 1. So we literally just have 1/4 here. Okay? So we actually have 20 times 1/4. That's a constant that we can bring out front. I'm going ahead and factoring out the 20, and I'm also factoring out the 1/4 because that fourth power doesn't do anything. And then we're left with our outer integral. So our outer integral goes from -1 to 2, and that's for x to the fourth dx. Okay? So we have 20 times 1/4. That 1/4 was me factoring out the inner constant. Brought that out front. And then we still have the integral of x to the fourth dx. And of course for this one, any other variable would be constant, but there is no other variable, so we don't have to worry about it. Okay, so 20 divided by 4 is 5. So we get 5 out front. And then for this integral here, we're going to once again use the power rule. So we add 1 to the exponent and we divide by the new exponent. So that's going to give us x to the fifth divided by 5. And we're evaluating that from x equals -1 to x equals 2. That's these numbers here that we originally had on the outer integral. Okay? So then we can obviously take the 1/5 out front, so the 5 and the 1/5 cancel out. So these cross out. And then plugging in the top number, we get 2 to the fifth. And then subtracting the function evaluated at the bottom number, we get minus -1 to the fifth. Okay, so 2 to the fifth minus -1 to the fifth. Alright, and that's going to give us 2 to the fifth. Well, let's see. 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. So 2 to the fifth is 32. And then -1 to the fifth, because it's an odd power, is going to be -1. But then these minuses are going to cancel out. Okay? So we're going to end up with 32 plus 1, which is 33. Okay, so our answer is 33. All right, and that's actually that's the entire iterated integral. Okay, and that was a relatively easy one, although most of the ones in your homework are not too bad. All right, so let's do a little bit harder one for number 2. Let's do another iterated integral. And for number 2, we're going to integrate the double integral from 0 to ln of 3 and from 1 to ln of 5. Okay, so from 0 to natural log of 3 and from 1 to natural log of 5. And our multivariable function here is e to the 3x plus y. And we're integrating this dy dx. So once again here, our inner integral is dy because the dy appears first. And then our outer integral is dx. And just in case you're not used to it yet, I'll circle the inner integral. And because that's the inner integral, these limits of integration for the inner integral are with respect to y. So this is the inner integral is going from y equals 1 to y equals ln of 5. Okay? And then the outer integral is dx. So that's going from x equals 0 to x equals ln of 3. That's just reading what it means. Okay, so we're going to be doing this inner integral first, the one in red. And because the integral is with respect to y, any other variable is constant. So here, the other variable is x, and x is constant. Okay, so for this one, x is constant. And remember, if you're integrating e to the u, the integral of e to the u is just e to the u. But here, we are going to have to use u substitution just to be safe. Okay, so what we're going to do is we're going to do u substitution, and we're going to let u equal the inner function. So here the inner function of e to the 3x plus y is just this inside part, which is 3x plus y. So here we're going to let u equal 3x plus y. Okay. And then if we find du dy, that's going to give us, well, the derivative of 3x, because x is constant, is going to be 0. And then the derivative of y is 1. Okay? So if we multiply both sides by dy, this gives us du equals dy. All right, so actually this u substitution might not have been necessary here, but it usually is when you have a composite function. So we're doing it just because it's usually necessary. But what we're going to have here is we're going to have the integral of e to the u times du. Since du equals dy, we can just plug in du here. So for our inner integral, we have the integral of e to the u du. And we still have our outer integral, but we're not going to worry about that until we're done with our inner integral. And this inner integral is going from 1 to ln of 5. But right now it's written in terms of u, so we don't want to write the numbers yet. Okay, but the integral of e to the u is just e to the u. Okay, so this is just going to give us e to the u. But we don't want it in terms of u, because u is a dummy variable. So what we have to do is we have to plug back in the original expression for u. So u was originally 3x plus y. So we have to plug that in down here. Okay, so instead of e to the u, we have e to the 3x plus y. All right, and we're going to be evaluating this inner integral from y equals 1 to y equals ln of 5. Okay, so from y equals 1 to y equals ln of 5. And notice I'm being lazy. I'm not even writing the outer integral yet because I want to just simplify this first. Okay, and I can simplify this. So what I can do is I can go ahead and plug in y equals ln of 5 and y equals 1. So plugging in the top number, we get e to the 3x plus ln of 5 minus e to the 3x plus 1. And then there's a little trick that we can use here to simplify this. I don't know if you remember this, but if you're adding inside of an exponent, that's the same as multiplying on the outside. So I can rewrite this as e to the 3x times e to the ln of 5 minus e to the 3x times e to the 1. Okay, and that's using a rule of exponents, which says that if you're multiplying exponents, that's the same as adding. So if you're multiplying outside of the exponents, that's the same as adding on the inside. So that's how we got from here to here. Okay, and then for the e to the ln of 5, the e and the ln cancel out. So these just cross out, and we just get 5. Okay? So what we actually have here is, we've simplified it a little bit. So this one's actually just going to be 5 times e to the 3x. Okay, so we have 5 times e to the 3x minus e times e to the 3x. And you might be wondering, well, why did I write it like that? Well, I know that 5 and negative e are both constants. So that means I can actually factor the e of the 3x out, and then the rest of this is going to be a constant. Okay, so if I factor out the e of the 3x, and I bring it out here, then we're going to be left with 5 minus e times e to the 3x. Okay? And then from here, what we have to do is we have to actually do the outer integral now. So I've been lazy about writing it, obviously, because I have to keep writing it over and over again. But we still have to do this outer integral. Okay, and this outer integral was dx. That's what I have circled in blue. And that's going from x equals 0 to x equals ln of 3. Okay, so now we're going to go ahead and do that here. So we're doing the outer integral from x equals 0 to x equals ln of 3. That's what I said, right? Yeah, x equals 0 to x equals ln of 3 of 5 minus e to the 3x dx, because our outer integral was dx. And like I said, 5 minus e is a constant, so we can just factor that out front. So if we factor out the 5 minus e, we get 5 minus e times the integral of e to the 3x dx. Okay? And that's going from 0 to ln of 3. And once again, since we're integrating with respect to x, the other variable y is constant, but this one doesn't have a y in it, so we don't have to worry about it. But if it had a y, that y would be considered constant. Okay, so what we have to do here is u substitution. And whenever you're doing u substitution, you always want to let u be the inner of your composite function. So here, the inner of our composite function is 3x, so that's going to be our u. So we're going to let u equal 3x and then taking the derivative, we get du dx equals 3. And then multiplying both sides by dx and dividing both sides by 3, we get dx equals du over 3. Now, why am I writing it like this? Why am I writing it as dx equals du over 3? Well, I have to plug it in here. So I have to plug in du over 3 in for dx right there. Okay, so it's a little bit trickier than the last u substitution. Okay, so but after we do all that, what we're going to end up with is we're going to have e to the u times du over 3. So we have the integral of e to the u times du over 3, and we still have a 5 minus e out front. So we can factor out the 1/3, bring that out front. Okay? So out front, we're just going to have 5 minus e all over 3. Okay, but the integral of e to the u, once again, is just e to the u. So this is just going to give us e to the u. But in this case, our u is different from the u that we used earlier. So for this problem, for this part of the problem, we said u is 3x. So we're going to want to plug that in here. So the integral of e to the u is e to the u, but we got to write it back in terms of x in order to plug in. So we're going to plug in 3x here instead of u. So we have e to the 3x. And of course, we're still evaluating this outer integral from x equals 0 to x equals ln of 3. Okay? So now we're ready to go ahead and plug in. And we can just leave this 5 minus e over 3 out front since it's a constant. So plugging in the top number first, we get e to the 3 times ln of 3 minus e to the 3 times 0. Okay, so that's plugging in the top number first and subtracting the entire function evaluated at the bottom number. Okay, and then what can we do to simplify this? Well, 3 times 0 is just 0, so this one over here is just going to be e to the 0, and any number to the 0 is 1. So this is just going to be minus 1 over there. And then over here, we can factor out the 3. So we can write it as e to the ln of 3 cubed. And then the e and the ln cross out. So we actually just get 3 cubed. Okay, so we have 3 cubed minus 1. And then for 3 cubed, 3 times 3 is 9, times 3 is 27. So that's going to give us 27 minus 1, which is 26. Okay, so that means we end up with, for our final answer, we're going to have 26 times the quantity 5 minus e all over 3. Okay? And that's our final answer. Okay, cool. So we've done some of the harder iterated integrals, and you get more practice on that on your homework. So I wanted to actually do an integral where we're doing a double integral per se, rather than just an iterated integral. But you're going to find that double integrals are pretty similar to what we've been dealing with. Okay, so new example. Example, evaluate the double integral. Evaluate the double integral over the given region R. Evaluate the double integral over the given region R. Okay, and here our double integral is written in a different way than the iterated integrals. So with an actual double integral, it looks a little bit strange the first time you see it. So you still write the double integral symbol, but instead of writing from x goes from whatever to whatever and y goes from whatever to whatever, you just write your region below it. So below it they just write capital R, which means we're doing the double integral over the region they give us. And here we're integrating our multivariable function is yx times cosine of x dA. Okay, and the capital A actually stands for area. So what we're really doing here is, when we're doing this double integral, is we're finding an area between curves. Okay, but the region they give us here, because of the title of the section is rectangles, this region is actually going to be a rectangle. So it won't actually be that hard. So here they're telling us that our region R is made up of two parts. First of all, we've got -5 is less than or equal to y is less than or equal to 5. And then we also have 0 is less than or equal to x, which is less than or equal to pi. Okay? So -5 is less than or equal to y is less than or equal to 5, and 0 is less than or equal to x is less than or equal to pi. Now this region R is actually a rectangle. How do I know it's a rectangle? Well, if you want, you can sketch it. You don't have to sketch it, but it's pretty easy to sketch. You've got your xy plane, and we know that x goes from 0 to pi. So here's 0, and then over here somewhere, here, let's see, 1, 2, 3, 4, pi would be right about there, 3 point something. So there's pi. We know x goes from 0 to pi. And then we know that y goes from -5 to 5. So it goes down to -5, 1, 2, 3, 4, -5, and it goes up to +5. 1, 2, 3, 4, +5. Okay? So our region is going to go just like this. Okay, and even with my terrible drawing skills, we can see that that's a rectangle. So this is R, this entire region here. Okay, so it's a rectangle, but because it's a rectangle, it's very easy to do this. In fact, we just create our own iterated integral, and they're even telling us the limits of integration. So the standard way to do this would be to just pick one of the variables as our inner integral and pick the other variable as our outer integral. So for example here, it would probably be pretty easy to integrate with respect to y first. So I'm going to make my inner integral with respect to y. So what we're going to do here is we're going to make an iterated integral. Make an iterated integral. Okay? And just following the approach we did before, we're going to make our inner integral be with respect to y, and our outer integral is going to be with respect to x. So we're going to have the double integral. Our inner integral goes from y equals -5 to y equals +5. And then the outer integral is going to go from x equals 0 to x equals pi. Okay, and then we still write our function. So our function is yx times cosine of x dA. But instead of writing dA, dA actually means the differential with respect to area. That just means area. And since we're finding the area of a rectangle here, that's why we're able to make an iterated integral. Okay, and we just use, since our inner integral is with respect to y, we're going to write dy first, and then our outer integral is with respect to x. So we write dx for the outer one. Okay, so that takes care of this region because it's just a rectangle. And in fact, all the regions in this section are rectangles, which makes them pretty easy because you can just set them all up as iterated integrals on your homework. Okay, but this one's going to be a little bit of work, so that's why I chose this one, because it's a little bit harder to do the actual integral part of it. So let's start with our inner integral. So for our inner integral, with respect to y, remember that x is going to be constant. Since we're doing dy, the other variables are constant, so x is constant. So that means I can actually just factor out this x cosine of x and just bring it out front, since that's all constant. Okay? And then we've got the integral well, all we're left with is y dy. And on the outside, we still have the integral of x cosine of x dx in black there. But why was I allowed to factor out the x cosine of x? Well, since x is constant, that means x cosine of x is also constant. That's why I was able to just factor that out. And now doing this inner integral, we're doing the integral of y dy. And the integral of y, using the power rule, we add 1 to the exponent, and then we divide by our new exponent. So we get y squared divided by 2. Okay? And we're evaluating this from y equals -5 to y equals +5. Okay? So plugging in the top number first, we get 5 squared over 2 minus -5 squared over 2. Okay? 5 squared over 2 minus -5 squared over 2. Okay, so the thing that's interesting about this problem is -5 quantity squared is going to give us +25. But we have a minus out front. So we've got 25 halves minus 25 halves. Which is actually just 0. Okay? But we still have the outside of our integral. Remember, the outside of our integral, we had the integral of x cosine of x dx. So this is a very unusual problem. Normally, if you were doing the integral of x cosine of x dx, you would have to do integration by parts, is the standard way to do it, which could be a lot of work. But here they have it set up so that since the inside is just 0, remember that any number times 0 is just 0. So here we're really integrating x cosine of x times 0 dx, but that's just the integral of 0 dx, because any number times 0 is 0, and the integral of 0 is just 0. So 0 is our answer. So it looked like it was going to be tricky, but They actually had it set up so it was kind of nice. It wasn't too bad.